Hi everyone, this is Maths World UK. I'm James Grime and today I'm speaking with Kit Yates. Kit is a mathematical biologist from the University of Bath, and today Kit has come to talk to us about the maths of epidemics because as I speak it is June 2020 and we're right in the middle of the COVID-19 epidemic, and so you hear these terms on the news: reproduction rate, R0, herd immunity, SAR models. And those are some of the things that Kit has come to explain to us today. In fact, Kit has been very much in demand over the last couple of months. So I started our conversation by asking Kit if he's been having a busy lockdown.
It's been pretty busy. I've got 2 kids to look after, so that's keeping me busy with the homeschooling stuff. One of them's just gone back to school, which is good. But yeah, I'm also been doing quite a lot of media work around trying to explain some of the basic ideas around the pandemic and around how the maths is helping to understand the spread of the pandemic.
It's kind of unique, isn't it? Because suddenly maths suddenly seems so relevant to the general public who may not even think about it after they've left school. Now suddenly maths is this big important thing in the news again.
Right, it's this answer to the question that teachers often hear. Why am I even doing this? Why am I learning about exponential growth? When am I ever going to use that in the real world? And then all of a sudden along comes this epidemic, and exponential growth is incredibly important, and understanding how we can slow that growth down, understanding mathematical models, is right at the forefront of everyone's conversations.
Yeah, and you keep hearing these terms, which I guess for most people they don't know what these terms are: exponential growth, R0 and SAR models and all these things. So today you're going to sort of take us through some of these basics.
Yeah, exactly. So I'm gonna start by just taking you through some of the really basic mathematical models that we use to understand the epidemics. So I will start by, I'll show you a few slides at the same time. So this is a shameless plug for my book. The reason I've put it on there is because the last chapter of the book is all about mathematical epidemiology. So a lot of the stuff that I'm going to be talking to you today is going to be directly taken from the book. So if you want more detail on anything that I say, then you can find a lot of it in there. So yeah, as you mentioned, one of the most basic models that we use to understand the epidemic is this SAR model. Sometimes you might have heard it called the SAR model in the news. The idea is we break the population down into different compartments. They're often called compartment models. And so that we have these 3 compartments: S for susceptibles, those are people who haven't yet had the disease; I for infected, so those are people that have the disease and can pass it on; and then R for removed, so this is a sort of euphemistic term for people who have recovered from the disease, hopefully with immunity, or people unfortunately who've died from the disease, but either way are no longer passing the disease on. And the way it works is that you get these susceptible people bumping into infected people. So this infectious person maybe goes and spends 15 minutes, 20 minutes chatting to this susceptible person without a mask on, and they can then infect that susceptible person. So they become red. And then as time progresses, then what you start to see is that people can recover. So the first infected person recovers, but maybe the second infected person meets another susceptible individual, they pass the disease on to them, and as time progresses, the second person recovers, and so on. And so one of the really crucial things to understand about an epidemic when it's first spreading initially is how many people on average will each individual pass the disease onto during the course of their infectious period. And that's what we call, at least at the start of the epidemic, that's what we call the basic reproduction number, or R0. So this number is latterly we've been calling it R, so it's often called the effective reproduction number once the epidemic's kicked off, but right at the start we call it the basic reproduction number. So it's really important to understand this number. It tells us whether the disease is going to take off or not. So if each new person that gets infected passes the disease on to more than one new person, more than one susceptible individual, then that means that the disease is going to take off. It's going to spread exponentially at first, at least. But if they pass the disease on to fewer than one other individual as time goes on during the course of their infectious period, then that means that the disease will die out eventually, because slowly the number of people who are currently infected will get fewer and fewer and fewer. And so these models, this basic model, has been used to represent things like norovirus in Belgium and things like swine flu in the Netherlands, and it was important to try and understand what this reproduction number was. So here's my little cartoon for you. You can see There's a person who's infected in red, and they go about the course of their weekly business during the course of their infection, and they meet 10 people in the first half of the week and they infect 2 of them. And then they meet another 10 people in the second half of the week and they infect 2 of them as well. And at that point, we say that the reproduction number, the basic reproduction number, is 4 because that person's infected 4 people during the course of their infectious period. So the understanding this basic reproduction number, especially at the start, can tell us lots of useful things about the epidemic. In particular, what you can do is calculate something called the final epidemic size. So we want to know, if we just let this disease spread through a population unchecked, how many people will be infected at the end, and how many people will survive unscathed by the time the disease burns itself out. So this is called the final epidemic size. We often call it S infinity, and the infinity is to indicate that a lot of time has passed, so when everything's burnt out. Now this final epidemic size, it's got quite a complicated formula. It involves this R0, the basic reproduction number. It's what we call an implicit formula because it has S infinity on both sides of the equation, and it's not straightforward to simplify it out, but we can solve it quite straightforwardly on a computer to find estimates of how many people will remain uninfected, susceptible at the end of the epidemic. So here are a few examples of diseases people will probably have heard of. So Ebola, SARS, COVID, of course, smallpox, polio and measles. So the basic reproduction numbers are given in the second column, and then you can numerically solve this equation to find out what the proportion of uninfected people is at the end of the outbreak. So with Ebola, it's actually got a relatively low basic reproduction number, about 1.5, although the reason why we're so terrified about Ebola is because it's got a high case fatality rate, which means of all the people that get it, a large proportion of them end up dying from the disease, which is why Ebola is particularly scary, even though it doesn't spread anywhere near as fast or as easily as COVID does. But if you do the calculation, then you find out that 42% of people, if you just let the epidemic spread unchecked, would remain susceptible at the end. So quite a high proportion, only about 60% of people would get infected. But then as the reproduction number starts to step up, if you look at SARS, that has an estimated reproduction number between 2 and 5. We don't have a really good handle on that, but that means that anywhere between 20% of people with the lower end of the reproduction number, or as low as 0.7% of people with the higher end of the reproduction number will remain uninfected. Similarly with COVID, it's as low as 6%. Smallpox, which has an R0 of 4, it's as low as 2%. Polio, it's 0.25%. And then measles, which is probably the most infectious, or one of the most infectious diseases we know of, with a basic reproduction number of between 12 and 18. So each individual during the course of their infectious period infects between 12 and 18 other individuals. Then that effectively everyone gets infected with the disease. Almost no one survives the disease. So that's a bit of the stuff that we can do with the reproduction number, but it's also useful to understand what goes into the reproduction number. So there are 3 different things that we can think about, which we can break the reproduction number down into these 3 different areas. So those 3 things are, firstly, the number of susceptible people in the population, or it's something to do with the density of the population. So if you're in a denser region, then the disease passes more easily. So the larger number of people there are, then the more easily this disease is going to transmit. The second thing is the transmissibility. So how easy is it to pass the disease between people? So we know that with COVID, it's relatively easy because you just have to be standing in close proximity to someone for 10 to 15 minutes and you have a relatively good chance of getting the disease from them. Whereas things like sexually transmitted diseases, for example, require close, intimate contact, and it's harder to spread those diseases. You can't get them just by standing next to someone for 10 or 15 minutes. So the transmissibility makes a real difference. And then the other thing is the recovery rate, or the recovery time for the disease. So the longer people are infectious for, the more likely it is that they're going to meet more people and pass the disease on to more people. So the longer the recovery time, or the shorter the recovery rate, the more likely it is that people are going to be able to pass on this disease. So those 3 things really feed into the reproduction number.
So it's not an inherent property of the disease itself. It's based on the environment that you're in.
Exactly. It makes a big difference what sort of environment you're in. So if you're in a very densely populated area, then disease transmission is much easier. It also varies from country to country. So, I've given these estimates of reproduction numbers for different diseases, but actually they're just estimates from one set of data from one country. There are lots of things that influence it, like density, like the age structure of the population, for example. Also things like, is social distancing naturally built into your culture? Is it more common to greet people with a handshake, or is it more common to greet someone with a bow from a distance? So all of these things feed into this reproduction number. And the reproduction number can be really useful because it tells us strategies for helping us to mitigate the effects of the disease. So back in 2001, when the UK had the foot and mouth disease, which is a disease in animals, one of the strategies that was used was culling, so killing infected animals. And the reason that works is because it effectively reduces the infectious period of those animals. It gives them less of a chance to pass the disease on to other animals, or between different farms, if you like. So that's part of the reason why it works. But actually, they didn't just kill infected animals in that outbreak. They actually also ended up killing uninfected animals. Which seems a bit strange and counterintuitive. What effect is that going to have? Well, actually, it reduces the susceptible population, which is one of the other factors which goes into the reproduction number. It means that there are fewer contacts between infected and susceptible people, fewer chances to pass the disease on. So what they did was a strategy called ring culling, where if you identify an infected farm, you put a radius around it. I think it was about 3 kilometres, and then any farm which sits in that radius, you unfortunately have to cull all the uninfected animals on those farms to stop the chance of the disease spreading out of that farm. Now, culling is clearly not ethical with a human disease. It's arguable whether it's ethical with an animal disease as well, especially a disease which is not fatal for those animals like foot and mouth. So we have to come up with other measures in order to control the disease. So one of the measures that we're seeing implemented at the moment is quarantining. So we're suggesting that people who come back from holiday in a foreign country quarantine, people who suspect they might have the disease quarantine themselves, even if they don't necessarily have it. And the reason that works is, again, because we're reducing the number of susceptible people. Even if they don't necessarily have the disease, it's good to isolate these people away. And also the transmission, we reduce the possibility of transmission between people. The other side of that is isolation. If you know you're sick, then you absolutely must isolate, and you need to stay away from everyone if you possibly can. Certainly only see people within your household. And again, that works in a slightly different way, but by effectively reducing the time for which you're infectious. Okay, you're still infectious, but you're now not meeting other people. So you're effectively reducing that length of period, which again feeds into R naught and can reduce the reproduction number. There's things like hand washing, which we know from previous flu pandemics is incredibly effective at reducing the reproduction number. If you wash your hands for 20 seconds 8 times a day, this is what was said in the study, then you can reduce this reproduction number by up to 3/4. So you can really reduce the spread of the disease. And for us, given that the estimated reproduction number of COVID was about 3 at the start, maybe a bit more, if we could reduce that by a factor of 3/4, that would take us below our critical value of 1, which would mean the disease would start out. So even simple hand washing, which is why it was being pushed so hard at the start, was really effective, as is physical distancing, or people call it social distancing. So staying sufficiently far away from someone, and what that does is it basically means that the transmissibility of the disease is massively reduced. You just don't have these susceptible infected contacts at close quarters if you stay 2 meters away from someone that you would otherwise have. So those are all sort of non-pharmaceutical interventions, they're called. So not giving someone an injection or a drug. There are antiviral medicines that people are trying to work on, which will hopefully reduce the severity of the infection, reduce the infectiousness, and reduce the time which people are infectious for. And there's also vaccination. So the next thing that I want to talk about is the possibility of vaccinating people. Now, for COVID, this seems like it's actually quite a long way away at the moment from being able to vaccinate people. Here we go. So the reason vaccination works is you reduce the total number of susceptible people in the population. So it just, again, denies the disease these susceptible infected contacts that it needs to spread through a population. So I'll show you another slide in a second, but these green people, these are again susceptible people. The red people are infected people, and then these outlined people, these are people who've had the vaccination and are now immune from getting the disease. So if we have a look at the what's called the effective reproduction number, so the reproduction number after you've taken an intervention, this person in red now is going about their daily business, and the first half of their walk around their week they infect 2 people, but in the second half of their walk they actually end up only infecting one other person, no other people in fact, because those people that they infected in the diagram that we saw before, they're now vaccinated, so they no longer have the disease, have the chance of getting the disease. So if you can do that, then you can reduce the reproduction number by half if you vaccinate half the population. And so we talk about this effective reproduction number, RE, which is in this case 2, because we reduced the number of people infected during the course of the infectious period from 4 down to 2. So vaccination can be incredibly helpful from that point of view. It can be so helpful that we can get something called herd immunity. Now, this is a little bit of a controversial subject in the UK because it was thought that the UK government was pursuing this idea of herd immunity, so trying to get enough people infected that they would build up immunity to the disease and that they would then not be able to pass the disease on, or people wouldn't be able to infect them. Of course, if you just get herd immunity by allowing the disease to spread unchecked through the population, then a large proportion of people get the disease, and unfortunately a large proportion of people will die. So that herd immunity policy that we were thinking about at the start in the UK, that was really quickly rescinded very early on. But there's another way to get herd immunity. Herd immunity just is about getting enough people immune that the disease can't spread anymore. So there's another way to get herd immunity, and the analogy that I like to give is to this sort of this situation where you're out in the rain. So you're a person, you're susceptible to a disease because you haven't had a vaccination, you're out in the rain, the germs are raining down on you and you can get this disease. Now, one of the most sensible things you can do is to get a vaccination, and that, in this analogy at least, is equivalent to putting on a coat. Okay, so you buy yourself a raincoat, and that does a pretty good job of keeping the diseases, or the disease that you've been vaccinated against, away from you. So this is good news. It's not perfect. Maybe your legs are still getting a bit wet. It could be leaky, so not all vaccines work for everyone. And it's also important to say that not everyone can get a vaccination. So if you're too old, or if you're too young, or you have some immune compromised situation, maybe you're pregnant as well, then you can't get a vaccination. So it doesn't work for everyone. Now, the good thing is that if you what would be better than having just a coat is if you had a massive umbrella as well to keep the rain well away from you. But umbrellas are really expensive, right? So you can't afford to buy an umbrella on your own. What you need instead is to get loads of people to buy raincoats, and then the store that sells the raincoats gives you an umbrella for free. So you need to get herd immunity. You can't get herd immunity on your own, but you need loads of people to get vaccinated, and if enough people get vaccinated, you get this umbrella, you get herd immunity, so that the disease can no longer spread through the population. And the great thing about herd immunity is that once you've got this umbrella, it doesn't just keep the people that have been vaccinated dry, it keeps everyone dry. So it keeps people who can't have the disease because they're too young or they're too old, so can't have the vaccination because they're too young or too old, it keeps them safe from the disease as well. So vaccination really is, if you've got a vaccine for the disease, the best possible way that we can wipe out a disease. So the question is then, how many people need to be vaccinated? How many people need to get a raincoat in order for this disease to be wiped out? So we can have a look with our original example. This time I'm vaccinating 3/4 of the population. Remember, our reproduction number was 4 at the start. So this time this person takes their walk and they pass the disease on to one new person during the course of their infectious period, because one of the people they would have passed it on to before is now vaccinated. And on the second half of their walk, they actually don't pass the disease on to anyone, and then they recover, and actually only one person was infected during the course of their infectious period, which means the effective reproduction number has been reduced down to 1, which is the critical value. Remember, if R is above 1, then the disease will take off, and if it's below 1, then the disease will die out. So this is good news, and it's no coincidence that by vaccinating 3/4 of the population, we were able to reduce the reproduction number by a factor of 4. We reduced the number of potentially susceptible people in the population by 1/4, by a factor of 4, and so we reduced the effective reproduction number from 4 down to 1, again by a factor of 4. So this tells us something about what's called the herd immunity threshold, or the critical immunisation threshold, which I've called Vstar on this slide. Again, it's got this formula, it has R0 in it. It's not hugely complicated this time, it's just 1 minus 1 divided by the reproduction number. So when the reproduction number was 4, we have 1 minus 1/4, which gives us 3/4. We need to vaccinate 3/4 of the population to wipe the disease out. So again, here are a number of R's, and I've just plugged this basic reproduction number into the formula there, and you can see that for Ebola, the basic number of people we have to vaccinate is actually quite low. It's just 1/3 of people before the disease is denied enough contacts between people to wipe them out. With SARS, it's between 50 and 80%, so a bit higher. With COVID, with a reproduction number which we're estimating to be about 3, it may be a bit higher than that. It suggests that you need to vaccinate 2/3 of the population. Smallpox, which had a reproduction number of about 4, this was in my opinion, one of the greatest success stories of the whole of humanity. It was being able to wipe out smallpox. So it has a reproduction number of 4, which means you have to vaccinate 3/4 of the population, just like our example before. And actually, when the WHO, the World Health Organization, eventually did wipe out smallpox in the 1970s, they went for a threshold of about 80% to give themselves a bit of leeway to play with. But it's amazing, like this is the only time we've ever managed to wipe out a disease, a human disease at least, off the face of the earth. Yeah, for me, one of the greatest achievements, and guided by this mathematical idea of herd immunity. With polio, which we're also getting close to eliminating, although ironically we're sort of struggling a bit at the moment because we're struggling to vaccinate people because people are staying at home and staying away from health centres, very wisely because of COVID. We're close to eliminating polio from the world, but you need to vaccinate a higher proportion of people because it spreads that much more. And then with measles, it's also not very good news. Like with the speed at which measles spreads, or the reproduction number that measles has, you need to vaccinate between 91 and 95% of the population. Now, amazingly, we actually get quite close to that. We have been quite close to that, and the UK and the US have actually both managed to eliminate measles from their country, although with the rise of anti-vaccination groups, people are tending to stay away from vaccination a little bit more. And actually the UK lost its measles free status last year because measles was circulating continuously in the UK for a period of a year, so we lost that status, and the US came very close to losing their eliminated status as well. So the reproduction number can have a significant impact on understanding the disease. And so there are all sorts of other applications for R0 and for mathematical epidemiology. I've really just touched on a very small number of them, and I'll finish with just a reminder of those. So like the reproduction number, the basic reproduction number R0, how fast it's spreading at the start, tells us how quickly a disease, or at least how, combined with how long it takes to pass the disease on, will tell us how quickly the disease spreads through a population. And knowing what goes into that reproduction number can also help us to suggest potential preventative measures, either pharmaceutical like vaccines and antivirals, or non-pharmaceutical interventions like social distancing, physical distancing, hand washing, things like that we've seen implemented at the start of this pandemic. These simple preventative actions, things like washing your hands, staying away from people, keeping that 2-meter distance, can help to stop the spread of the disease. And then finally, this idea, this really mathematical concept of herd immunity. If you can vaccinate enough people in the population, then you can protect people in our society who can't have those vaccinations. Then that's a really important mathematical concept which comes out of all of these models. And I'll just finish by saying, if you do want to find out more about any of these concepts and go a bit more deeply, then you can find it in this book. Yeah.
Thanks very much, Kit. One of the things I was interested in that you said was that vaccines are not 100% effective on everyone. So I was thinking about how effective they have to be, but I guess you can just adjust for that. The important thing is that your reproduction number has to be less than 1.
Yeah, exactly. So yeah, if so there are, vaccines can be what's called leaky, so they don't work for everyone. And in fact, interestingly, there was this big measles outbreak in the US at Disneyland back in 2014, and it was found that a significant proportion of the people who ended up getting measles from the outbreak had actually had one shot of the vaccination, not two, which you need to have to get the proper immunity. But some people had had one of the shots of the vaccination and still managed to get the disease. So not all vaccines are perfect, but they are the best way we have of wiping the disease out. And as you say, you can adjust for what proportion of people do I need to vaccinate, given that there's some number of people that won't have the disease, in order to still achieve that proportion of people who are immune to the disease, so that we can gain herd immunity. Yeah.
And do the models that we're using, do they account for the people who are not following guidelines?
Right, so certainly the Imperial College model, which is the big one that many people will have heard from Neil Ferguson in his group, they absolutely say, well, we know that we hope people will be doing this physical distancing, we hope people will stay at home, but actually we suspect that maybe only 75% of people will actually do that. So they take into account, but it's really difficult, obviously, to quantify how well or how badly they're doing on those stats. And the other thing to say is that the models that they're using well, at least the Ferguson group at Imperial are using significantly more complicated models than the SAR model that I showed you. Not many proper mathematical epidemiologists would use the SIR. Some would use what's called the SEIR, where you have another class of people who are exposed to the disease, so they have the disease but they can't yet pass it on, which is much more realistic for COVID. We think there's about a 4.5 day period when you have the disease, the virus is replicating inside you, but you can't yet pass it on. Other people look at asymptomatic carriers, so we have another class called the carrier class, where people have the disease but they're not showing symptoms, so you don't know that they have the disease, but they can still pass the disease on. And again, with COVID, there's thought to be a short asymptomatic period before people show symptoms, so half a day when you can pass the disease on but you don't yet know you've got it. And also there's suspected that there are also asymptomatic carriers, so people who never show signs but can also pass the disease on. So these models can get arbitrarily more complex if you want them to, but you need to ask the question, can I get the right parameters, to the right data, to make sure that my model's actually doing what reality is telling me?
How are we measuring the spread? So we have a COVID test, but also there's the possibility of false negatives and false positives, and also this has been done by people at home, unprofessional people, or non-professional people, should I say, doing it at home. How can we account for that?
So sort of two different parts to that question. Firstly, how are we measuring the spread? Well, at the moment we have to look at things like number of deaths and try to back calculate from those number of deaths how many people were infected at a given time. This is a really difficult thing to do because you need to know a distribution of infection time to death time, and that distribution is not really well known at the moment. So we're trying to do something called nowcasting, where we look at tests and cases that we think we have, although we know we're missing a lot of people in the testing. We know we're not testing everyone at the moment, and then we have to do what's called nowcasting, which is effectively predicting the future but about now instead of forecasting, to try to understand what the current number of cases look like and how that's changing, to give us an estimate of the R number. But you're absolutely right that like in terms of cases, it's really fraught trying to understand how many cases there genuinely are in the population. So as you mentioned, people doing their own tests or people being tested at slightly the wrong time when they haven't got a high viral load can lead to false negatives in these swab tests. And that can be really dangerous when you have a high proportion of people in the population that you're testing who have the disease, so in a hospital setting, for example. And it can turn out that the false negatives can massively outweigh the number of true negatives when you're testing people. So you might end up sending people that have the disease into a non-COVID ward when they actually do have the disease. It's suggested that perhaps 30% of tests are false negatives when they give a negative result. So it's not great news from that point of view. The other side of testing that we're going to be relying on potentially more in the future is antibody testing to know whether people have had the disease or not. Have they got antibodies against it? And again, this time the problem is the opposite. When you're testing a large number of people in the population who don't have the disease, we think our prevalence is below 10% of people in the whole population who've had the disease at the moment. And your test lacks a bit of what's called specificity, i.e. it gives you some non-trivial rate of false positives, then in this situation the false positives can massively outweigh the true positives. So we see this sort of same problem when we're doing screening for breast cancer or prostate cancer. And so yeah, the false positives can massively outweigh the true positives, which is obviously problematic if we're using these tests to say, yeah, you can go back to work because you've got antibodies, when in fact those people haven't got antibodies. We release these susceptible people into the population, they can then get infected without knowing it, spread the disease, and we can kick off potentially a second wave. So understanding the intricacies behind the mathematics of testing false positives and false negatives is going to be really important going forward in the epidemic.
Can we try and end on a positive note? Is there any good news coming?
I think that there is lots of good news. Like, lots of different countries have been trying different strategies out. Sweden, for example, have been going for this herd immunity, and their health system, which admittedly has more capacity than ours does, hasn't been overwhelmed, but they have had significantly higher numbers of people dying than in other Nordic countries. But the potential is that they might be able to come out of lockdown. If you look at countries like New Zealand, that's for me the real positive news story. They're effectively going back to normal. Of course, they're not. They're being very careful about who's coming into and going out of the country, but they have no deaths and they have no new cases. So there are lots of positive things. There's also lots of positivity about developing vaccines as well. So although it seems like it's a long way away, this isn't going to last forever. It is going to change how our lives are, but it isn't going to last forever, and eventually we will be able to kick this disease. I'm hopeful of that, at least.
I want to say thanks again to Kit for coming in and speaking to us, and if you want to buy Kit's book, we'll put a link in the description, and until next time I'll say stay safe, stay curious.